This first lecture is based on Introduction to Calculus, just as the name suggests. Calculus is a branch of mathematics that has two main branches: the differential calculus and the integral calculus. These two branches of calculus, they're basically reverse processes of each other. So what you do when you're dealing with the differential calculus, the process is called differentiation. And over here, the process is called integration. So let's assume that we have a function f of x, and you perform the process of differentiation on that function. You might end up with some other function. Let's call it g of x, whatever this process of differentiation entails. Because these two processes reverse each other, if you were to take this function g of x and perform the process of integration on it, guess where you end up? Right back at f of x. So that's a broad overview of the two main branches and how they relate to each other. Now, we're going to start with the differential calculus. What does that mean? Differentiation. I'm going to give you a very simple example that I always use to explain this concept. If you were to give a strict definition of differentiation, the differentiation can be thought of as the rate of change of one variable with respect to another. Rate of change of one variable with respect to another variable. So here's a pretty simple example I like to use. Here's a balloon, and you're blowing air into that balloon. And we're going to assume that this balloon is spherical. So it has a radius of r. I'm getting accustomed to using this thing. Yes, it has a radius of r. It has a volume, v. What else? It has a surface area. Let's call the surface area A. What else? The pressure inside the balloon. Let's call that P. And let's take two other variables. The mass of air inside the balloon. Let's call it M. And last but not least, time. These are all variables. The actual act of blowing the balloon up, as the balloon is being blown up, its volume is increasing, its radius is increasing, its surface area is increasing, the pressure inside is increasing, the mass of air, time of course, is clearly increasing. If we wanted to measure the rate of change of any one variable with respect to another, effectively we would be finding a derivative. We'll be finding, for example, if I wanted to know the rate of change of volume with respect to radius, the notation for this, it's pretty straightforward. Because we have the two variables that we were working with, rate of change of volume, let's call the volume that we already did. The volume is V and the radius is R. The rate of change of volume with respect to radius, the notation for that would be dV dr. And I can pick any two variables and find the rate of change of any one with respect to any other one. So for example, the rate of change of, let's pick surface area. S with respect to time. T. Well, guess what the notation for this would be? ds dt, and so on. Now let's try one more. The rate of change of pressure with respect to mass. Then that would be dPdm. Etc., etc., etc. In general, because in this math course, your two most favorite variables would be y and x. If I wanted to find the rate of change of y with respect to x, I'm still getting accustomed to using this thing. If I wanted to find the rate of change of y with respect to x, the notation for that will be dy dx. And you'll be seeing this particular expression representing differentiation quite a bit. Okay, so if I were to go back up here, this is one way to think of differentiation. You can think of it as a rate of change of one variable with respect to another. At this level, sometimes as you go deep into calculus, you'll realize that you have what's called multivariable calculus, where you have a bunch of things, like all these variables I have here, for example. And you could have a function that includes more than two of those variables. And then the process of differentiation will be a bit different. But certainly for this math course, we'll only be dealing with two variables at a time. In general, your y and x. Okay. A second way to think of differentiation, we think of differentiation as giving rise to what's called a gradient function. dy dx. You'll be calling that your gradient function. And you'll be using that in your applications. You'll be using that in applications. Typical application would be, can you find the equation of a tangent or curve at a point? And things like that as we go along. And of course, the third way, another way of thinking of differentiation, we kind of mentioned it at the top, but I'll mention it again. Differentiation, you can think of it as a reverse process of integration. Summarizing, rate of change of one variable with respect to another. Differentiation gives rise to a gradient function. Differentiation is a reverse process of integration. Those are the three main ways in which we're going to be using it. Now, notice that up to this point, I haven't actually told you how you actually go about differentiating a function. The process of differentiating a function will depend upon what type of function you have. The rules for differentiation differ for different types of functions. If I wanted to differentiate a polynomial function, the rules for that would be different than if I wanted to differentiate an exponential function. It would be different from if I wanted to differentiate a log function. It would be different from if I wanted to differentiate a trigonometrical function, etc., etc., etc. We are going to start with the most basic type of function that we've been working with in this course, and clearly that is the polynomial function. Differentiation of the polynomial. Now, what I'm going to do is we're going to quote the rule. We're going to start with one basic rule for differentiating a polynomial, and then we're going to apply it to in different scenarios. So here's the rule. Once your function looks like this, y is equal to a times x to the power n. Your x and your y are your variables, of course. A and n are constant. Then if I wanted the rate of change of y with respect to x, the notation would be represented as dy dx. And the rule is you drop the n times the a times the x, and then you subtract 1 from the power. You can't have a rule that's simpler than that. Says I, differentiation of a polynomial function. So let's jump right in and start experimenting with a couple of different cases. Y is equal to 3 times x to the 5th power. Okay, what's wrong with my pen? It's not writing. There. 3x to the 5th. If we apply that rule exactly as it's written there, then dy dx, the rate of change of y with respect to x, would be given by 5 times 3 times x to the power 5 minus 1. Again, you can't get a rule simpler than that. If you tidy that up, the result becomes dy dx is equal to 15x to the 4th. Now what we're going to do, we're going to eliminate this intermediate step almost immediately. The 5 times the 3, because everybody can multiply 5 by 3 in their head, and then subtract 1 from the power. So let's try another one. Y is equal to 7x cubed. Okay. drop the power, so 7 by 3 would give you 21. dy dx would be equal to 21 times x to the power, and you subtract 1 from the power in the function, you get to the power 2. Pretty straightforward still. Very important to note, differentiation satisfies the distributive law. That is, differentiation distributes over addition and subtraction. It satisfies the distributive law for addition and subtraction. So, if let's say you had a polynomial function made up of parts that are added and subtracted, y is equal to 5x cubed minus 3x squared plus 2x minus 7. You simply apply the rule as shown up here, y is equal to ax to the n. You apply it to each individual part of this function, and you simply add and subtract the pieces back together. So let's see. dy dx, the rate of change of y with respect to x, will be, drop the power in the first case, 5 3s, 15, x to the power, 3 minus 1 gives me a power of 2, minus 3 2 6, x to the power, drop 1 from the, subtract 1 from the power, you get 6 times x to the power 1, plus 2x, drop the power on the x is 1, clearly, so that would be 2 times 1 is 2, times x to the power 0. I think everybody knows what that is. And then how about the constant? How do you differentiate a constant? What's the result that you end up with when you differentiate a constant? Well, let's think about that for a second. A constant doesn't change. A constant remains fixed, has a fixed value. 7 will always be 7, or minus 7 if you want to look at it like that. That value will always be the same. If you keep in mind the first way we thought of differentiation, here it is somewhere up here. Differentiation can be thought of as the rate of change of one variable with respect to another variable. So, because differentiation measures rate of change and a constant does not change, a constant has 0 rate of change. What's the bottom line? What's the summary of that idea? Whenever you differentiate a constant, whenever you differentiate a quantity that cannot change, the result is 0. Because differentiation measures rate of change, constant does not change, therefore constant has 0 change and 0 rate of change. If you tidy this up, dy dx is equal to 15x squared minus 6x plus 2. That's not too bad. I'm going to do a couple more examples, and then I'm going to give you a worksheet. Sometimes you have to simplify the function to put it in the polynomial form first. For example, if I wanted to differentiate y is equal to 3 divided by root x. Well, that doesn't quite look like a polynomial, and what's all this square root business? Well, we certainly know our laws of indices. We can rewrite that function in the form, we can rewrite that function in the form y equal ax to the n. Yes, we can. If you first of all get rid of the square root by rewriting it as 3 upon x to the power of a half, and then throwing the denominator up into the numerator. Jeez, I'm still trying to get accustomed to using this thing. You end up with y is equal to 3 times x to the power minus a half. And it certainly looks like it's in the form y is equal to a times x to the n. Once it's in that form, you apply the rule as it's given. So at this point, this is where we differentiate. And by the way, everything in between here is we were just simplifying it. So we still call the function y. It's only at the point where you actually perform the process of differentiation. Then you can write dy dx. Here is where we're finding dy dx. or the rate of change of y with respect to x. That will give me 3 times minus a half. I'll spell this one out. 3 times minus a half times x to the power minus a half, but remember you're still subtracting 1 from the power. Let's tidy this up a little bit. dy dx is equal to minus 3 halves times x to the power minus 3 halves. Generally speaking, I try to rewrite a function. It's correct as written, but it doesn't look tidy. So we're going to rewrite it with a positive power by dropping that the x to the power minus 3 halves back into the denominator. So this looks like minus 3 upon 2 x to the power positive 3 halves. And then last but not least, we're going to write it back with a square root. End result, dy dx is equal to minus 3 upon 2 times the root of x cubed. That looks pretty good. Let's try one more. Actually, let's try 2 more. Suppose the function looks like y is equal to 4x minus 3 all squared. Remember, at this point, there's only one rule of differentiation you know, based on what I'm teaching you in this tutorial. So the only way you can apply that one rule is if each part of this function looks like a polynomial, not like an entire expression raised to power. So what we want to do is expand the brackets until we learn other rules that will allow us to differentiate this without expanding the brackets. But at this point, based on that one rule we know, we'll have to expand the brackets. And everybody should know how to do this with no issues. Square the first, 16x squared, 2 times first times the second, 2 4 is 8, 3 is 24, minus 24x, plus 9. Now that the function looks like a full polynomial, or a standard polynomial, dy dx can now be written as 16 2's, 32x, minus 24 times 1, minus 24, oops. Minus 24 times x to the 0, which is 1. And of course, again, whenever you differentiate a constant, 9 is indeed a constant, you get 0. dy dx in this case is therefore that expression. Last example. Y is equal to x root x minus x squared times root x. We're going to apply a lot of indices here. So we still write y because we aren't differentiating as yet. We want to make sure that each part of this function looks like a polynomial. Y is equal to x times root x can be written as x to the half minus x squared times x to the half. I have to do a little more simplification. X times x to the half, same base, and you multiplying, you add the powers. Everybody knows that. Even I know that. This is x to the power 3 halves minus, and this would be x to the power when you add the power, 2 powers, 2 plus a half, x to the power 5 halves. Now the function looks like each part looks like it's in the form a x to the n. You differentiate, dy dx is equal to drop the 3 halves times the coefficient in front, which is 1. 3 halves times 1 is 3 halves. X to the power, subtract 1 from the power, you get 3 halves minus 1 is a half. Oops. Dropping back on my subtraction there. Minus 5 halves, drop that power. X to the power 5 halves minus 1, that gives you the power 3 halves. And if we tidy this up a little bit, this looks like 3 root x upon 2 minus 5 root of x cubed upon 2 dy dx is equal to, give it a common denominator, 3 root x minus 5 root x cubed all upon 2. And I'll leave it like so. A pretty decent way to leave it. And this brings me to the end of my first tutorial on calculus. Let me set you up with a worksheet. Differentiation worksheet. Number 1. 1. Y is equal to 7x to the 4th plus 3x squared minus 4. Number 2. Y is equal to 2x minus 3 all cubed. Number 3. Y is equal to x plus 1 all squared x plus 1 all squared times 4x minus 3. Y, geez, I keep doing that. Number 4. Y is equal to this power. Yes, let me give you some of these. I can spell it wrong. 4 minus 2x plus 7x squared minus 3x cubed. Number 5. Y is equal to 4 root x minus 3x squared divided by please stop this nonsense. Where's my worksheet? 4 root x minus 3x squared upon x to the power 3 halves. And one more to keep you busy and out of trouble. Number 6. Y is equal to square 2x minus 1 times 7x plus 3 all squared. Try another one. Y is equal to let me see how you're going to deal with this. Y is equal to 1 plus t plus t squared all upon 2t. Remember, the variable doesn't have to always be y and x. Clearly, for this one, because the variables of interest are y and t, when you differentiate, excuse me, when you differentiate the notation, it's obviously dy dt. And we're going to call it a wrap for this first worksheet. I'll be updating these or giving you additional worksheets as the week goes on, and an additional theory, of course. By the way, you would have noticed that I started with calculus I wanted to get away from, I know when we start, the last time we met, we were working on functions. We were probably 2/3 of the way through that. I wanted these tutorials to start from fresh with something we hadn't done before. So that's that. All right. I'll be posting this shortly.